Hey, sleepers. Tonight, we're drifting towards the edge of existence, to a place where reality itself might just burn. Imagine a silent, velvet expanse. In this darkness, a single point of gravity so immense it pulls in the starlight around it, not like a vortex, but like a soft, final whisper. The light doesn't scream as it vanishes. It simply ceases to be, its journey ending at a boundary we can only describe with mathematics and dreams. This is the edge of a black hole, and it is here, in this perfect quiet, that a fiery debate rages. So before you get comfortable, take a moment to like the video and subscribe. It helps our sleepy community grow, and it lets us know you're enjoying these journeys into the cosmos. While you're there, we'd love to know where you're listening from. Please share your city or country and the local time in the comments below. It's always so wonderful to see how far these stories travel, connecting us all under the same vast, starry sky. So close your eyes, take a deep breath, and get ready to drift off as we explore the black hole firewall that burns reality. Our story begins not with a fire, but with a thought. A beautiful, revolutionary thought in the mind of a man named Albert Einstein. In the early 20th century, the world of physics was a neat and tidy place. Gravity was a force, a simple pull that one object exerted on another, like a string connecting the earth and the moon. But Einstein, with his famously unruly hair and a mind that saw the universe in a completely new way, wasn't satisfied. He imagined what it would be like to fall, not just from a building, but to fall freely, endlessly, through space. In his famous thought experiment, he pictured a man in an elevator in deep space, far from any planet. If the elevator was pulled upwards by a rope at a constant acceleration, the man inside would feel his feet pressed to the floor. He would feel gravity. He couldn't tell the difference between this acceleration and the gravity of a planet like Earth. This was his equivalence principle, the idea that gravity and acceleration are two sides of the same coin, indistinguishable from within a closed room. This simple, elegant idea led to something extraordinary. It led to the theory of general relativity. Einstein proposed that space and time are not separate, static things. They are woven together into a single dynamic fabric. He called it spacetime. And massive objects, like stars and planets, don't just sit in this fabric. They bend it. They warp it. Imagine a vast, flat trampoline. This is our spacetime. Now, place a bowling ball in the center. The trampoline sags. It creates a curve, a dip in the fabric. If you roll a small marble nearby, it won't be pulled by the bowling ball. Instead, it will follow the curve in the trampoline, circling the bowling ball in a smooth, elegant orbit. That, Einstein said, is gravity. It is not a force. It is the geometry of the universe. It is the shape of spacetime itself. This was a profound shift in understanding. It explained why planets orbit the sun in graceful ellipses. They are simply following the straightest possible path through the curved spacetime created by the sun's immense mass. For a while, this beautiful theory seemed to explain everything about the cosmos on a grand scale. But within Einstein's own equations, there was a ghost. A prediction so strange, so unsettling, that even Einstein himself was reluctant to believe it. The equations suggested that if you could squeeze enough mass into a small enough space, the curve in spacetime would become infinitely deep. It would become a bottomless pit. Not a pit in space, but a pit of space. A region where the fabric of spacetime is so severely warped that the escape velocity, the speed you would need to break free, becomes greater than the speed of light. And since nothing in the universe can travel faster than light, nothing that crosses this boundary can ever get out. This was the birth of the idea of a black hole. For a long time, they were just a mathematical curiosity, a spooky what-if scenario. But then, astronomers began to see evidence of their existence. Stars orbiting, nothing. Immense gravitational effects coming from points of complete darkness. The ghost in the machine was real. A black hole is born from the death of a truly massive star. When a star many times the mass of our sun runs out of fuel, it can no longer hold itself up against its own colossal gravity. It collapses catastrophically in on itself. The star's matter is crushed down into an unbelievably tiny point, a region of infinite density called the singularity. But we can never see the singularity. It is forever hidden from us, shrouded by a boundary called the event horizon. The event horizon is a fascinating and gentle concept in Einstein's theory. It's not a physical surface. You couldn't touch it or stand on it. It is simply a point of no return. Imagine a peacefully flowing river. The water moves slowly at first, and you can easily paddle your canoe against the current. But as you drift downstream, the current gets stronger. At some point, you cross an invisible line where the river is flowing faster than you can possibly paddle. No matter how hard you try, you can only go one way, downstream. The event horizon is like that line in the river. It is the boundary where the current of spacetime flowing into the black hole becomes faster than the speed of light. According to Einstein's general relativity, an astronaut falling into a black hole would experience nothing special as they crossed the event horizon. There would be no bang, no flash, no jolt. One moment they would be outside, able to send a signal back to their ship. The next moment they would be inside, past the point of no return, but still feeling perfectly fine, floating in the quiet of their freefall. This is a direct consequence of the equivalence principle. In freefall, you feel no gravity. So at the very moment of crossing the horizon, our brave astronaut should feel no drama. Let's call this the no drama rule. From their perspective, their journey towards the center would continue, peacefully, for a little while longer. The universe outside would appear to speed up, and eventually, the immense gravitational forces near the singularity would become overwhelming, a process physicists gently call spaghettification, as the astronaut's body would be stretched into a long, thin strand. But at the edge, at the horizon itself, everything should be calm, smooth. This picture of a gentle, uneventful crossing is a cornerstone of general relativity. And for a long time, this was the accepted story. Black holes were simple, elegant monsters. So simple, in fact, that a famous idea called the no-hair theorem emerged. It was humorously named by the physicist John Wheeler. The idea is that once a black hole forms, it loses all of its complex features. It doesn't matter if it was made from a star, a planet, or a giant collection of teacups. Once it settles down, a black hole is bald. It has no hair, no complicated features to describe it. All you need to know to describe it perfectly are three things: its mass, its spin, and its electric charge. That's it. All the intricate information about what fell inside is, according to classical physics, hidden away forever, lost behind the one-way door of the event horizon. The black hole is a perfect cosmic vault, a silent, simple object defined only by these three numbers. And for decades, this was our understanding. a universe governed by the graceful geometric laws of Einstein, where black holes were the final, quiet resting places of matter, their secrets locked away for all time. But another revolution was brewing, one that would come from the world of the very, very small, and it would threaten to set this peaceful picture on fire. For much of the 20th century, physics was a tale of two kingdoms. On one side, you had Einstein's general relativity, the majestic king ruling over the vast scales of planets, stars, and galaxies. It described a smooth, predictable geometric universe. On the other side, you had quantum mechanics, the chaotic, magical queen of the microscopic realm of atoms and particles. This world was not smooth. It was jittery. It was not predictable. It was probabilistic. It was a world of uncertainty, where particles could be in multiple places at once, and where empty space was not empty at all. This empty space, according to quantum theory, is a fizzing, bubbling sea of activity. It's often called the quantum foam. Imagine for a moment a bank that allows you to borrow money for an infinitesimally short amount of time, as long as you pay it back almost instantly. The universe, at the quantum level, does something similar with energy. It allows a tiny bit of energy to be borrowed from the vacuum to create a pair of particles. A particle and its twin, an antiparticle. They pop into existence for a fleeting moment, and then, before the universe can notice the debt, they collide and annihilate each other, disappearing back into the foam. These are called virtual particles. They are constantly winking in and out of existence, everywhere, all the time. Usually, this dance is perfectly balanced, and nothing much comes of it. But in the 1970s, a brilliant physicist named Stephen Hawking started to wonder what would happen if this dance occurred right at the edge of a black hole's event horizon. Stephen Hawking, working from his wheelchair, his mind soaring through the cosmos, combined the two great theories of physics in a way no one had before. He applied the strange rules of quantum mechanics to the immense gravity of a black hole. And what he found was astonishing. It would change our view of black holes forever. He wasn't entirely alone in this thinking. A few years earlier, an Israeli physicist named Jacob Bekenstein, then a graduate student at Princeton, had made a startling suggestion. He argued that a black hole must have entropy. Entropy is a measure of disorder, or more precisely, the amount of information you need to describe a system. Bekenstein proposed that the surface area of a black hole's event horizon was a measure of its entropy, of all the information it had swallowed. At the time, many physicists, including Hawking, were skeptical. For a black hole to have entropy, it would have to have a temperature. And if it has a temperature, it must radiate heat. But everyone knew that nothing, not even heat, could escape a black hole. It seemed like a contradiction. But Hawking, spurred by Bekenstein's idea, decided to do the full calculation. He imagined these pairs of virtual particles popping into existence right at the event horizon. Every now and then, something peculiar would happen. A pair would be created such that one particle would fall into the black hole, while the other would be just outside the horizon. The one outside would be able to escape. From a distance, it would look like the black hole itself had just spat out a particle. The particle that fell in a strange quirk of quantum accounting, is considered to have negative energy. Think of it this way. When you create something from nothing, you need to balance the books. The escaping particle has positive energy. So the particle that falls into the black hole must have negative energy to cancel it out. When this negative energy particle is swallowed by the black hole, It reduces the black hole's total mass and energy. E equals mc squared after all. Less energy means less mass. Slowly, particle by particle, the black hole would radiate its energy away. It would glow ever so faintly with a heat that came to be known as Hawking radiation. This meant that Bekenstein was right. Black holes have a temperature, and they radiate. And most shockingly of all, this meant that black holes are not eternal. They evaporate. Over unimaginable timescales, trillions and trillions of years for a typical stellar mass black hole, they will shrink, leak away their mass, and eventually, in a final tiny puff of radiation, disappear completely. Let's visualize this for a moment. Picture the event horizon not as a sharp line, but as a misty shore on a vast, dark ocean. And all along this shore, tiny, shimmering pairs of fireflies wink into existence. Most of them appear, touch their lights together, and vanish. But right at the water's edge, a pair appears. One firefly flits inland, over the dark water, and is lost from sight. The other, its partner now gone, flutters away, out into the night. An observer far away sees only this lonely firefly, a tiny speck of light seemingly born from the dark ocean itself. This is Hawking radiation. Each escaping firefly carries away a tiny bit of the ocean's essence, and over eons, the ocean itself slowly fades away. This discovery was monumental. It was the first real bridge between general relativity and quantum mechanics. It showed that when you mix the two, black holes are not the simple, static objects we thought they were. They are dynamic. They have a temperature. They glow. And they die. It was a beautiful, elegant result. But in solving one problem, Hawking had unwittingly created a new one. A paradox so deep and so profound that it has troubled physicists for nearly half a century. A problem that threatens the very foundations of what we know about reality. It is called the black hole information paradox. To understand the information paradox, we first need to understand what physicists mean by information. It's not quite the same as the everyday meaning, like the words in a book or the data on a hard drive. In quantum mechanics, information is the complete description of a physical system. It's the precise state of every single particle, its position, its momentum, its spin. It's the unique, fundamental blueprint of that object. And one of the most sacred, unbreakable rules of quantum mechanics is that information can never, ever be truly destroyed. It can be scrambled, hidden, or rearranged, but it is always conserved. Let's use a simple analogy. Imagine you have a book. The information is in a specific arrangement of ink on the pages. Now you burn the book. To our eyes, the information is gone. The story is lost. But a physicist would tell you that's not true. If you could, with perfect precision, collect every single particle of ash, every molecule of smoke, every bit of heat and light that was released from the fire, you could, in principle, reverse the process. You could reconstruct the exact state of the book before it was burned. The information isn't destroyed. It's just been explosively redistributed and scrambled into a much more complex form. The universe, according to quantum mechanics, keeps a perfect record of everything. This principle is sometimes called unitarity. It's the idea that the present state of the universe is a direct, reversible consequence of its past state. Now, let's bring this back to our black hole. You take your book, and instead of burning it, you drop it into a black hole. The book crosses the event horizon and falls towards the singularity, its information joining the jumbled mess inside. According to general relativity, that information is now locked away from the rest of the universe forever. That's already a bit strange, but we could perhaps live with it. We could just say the information still exists. It's just inaccessible, stored inside the black hole's vault. But then, along came Stephen Hawking. His calculations showed that the black hole evaporates. It slowly radiates its mass away in the form of Hawking radiation. And eventually, the black hole disappears completely. So, what happens to the information from the book that we threw in? Where did it go? This is the heart of the paradox. Hawking's original calculation suggested that the radiation coming out is purely thermal. It's random. It's like the hiss of static on a radio. It's a jumble of particles whose properties are completely independent of what fell into the black hole. The radiation from a black hole made of books would be identical to the radiation from a black hole made of teacups. The escaping particles carry no memory, no trace of the objects that created the black hole in the first place. So, when the black hole is completely gone, vanished in a final puff of radiation, the information that it contained, the story in our book, seems to be gone with it. Not just scrambled, but utterly erased from existence. This is a catastrophic violation of the rules of quantum mechanics. It means that the universe does not keep a perfect record. It means that information can be permanently destroyed. This is the information paradox. It created a deep and fundamental conflict between our two best theories of the universe. General relativity, with its smooth event horizon, says the information falls in and gets trapped. Quantum mechanics, with its sacred law of conservation, says the information cannot be destroyed. And Hawking radiation, which is born from the marriage of these two theories, seems to say that the information both falls in and is ultimately destroyed when the black hole evaporates. This is not a small discrepancy. It's a full-blown contradiction at the heart of modern physics. It tells us that somewhere, in our understanding of gravity, or quantum mechanics, or both, there is a serious mistake. Physicists wrestled with this problem for decades. It was a slow-burning crisis. Perhaps some argued Hawking's calculation was incomplete. Maybe there were subtle correlations in the radiation, a hidden message in the static that carried the information out. If you could collect all the Hawking radiation over trillions of years, maybe you could decode it and reconstruct the book. This seemed like a plausible way out. The information isn't lost. It just leaks out very, very slowly, encoded in the escaping particles. This idea preserved the laws of quantum mechanics. But it would lead to an even stranger, more violent paradox of its own. It would lead to the firewall. The stage for the firewall was set by years of debate over the information paradox. By the early 2012s, many physicists had come to accept the idea that information must escape the black hole, encoded in the Hawking radiation. It seemed the most conservative option, the one that saved the bedrock principles of quantum mechanics. But they hadn't fully worked through all the consequences of this assumption. It felt like they had patched one leak in their boat, only to find that the patch itself was causing an even bigger hole to appear elsewhere. In 2012, 4 physicists came together to explore these consequences in detail. They were Ahmed Al-Hiri, Donald Miralf, Joseph Polchinski, and James Sully. They would later be known by the acronym of their last names. P.S. They weren't trying to invent a radical new theory. They were simply trying to be very careful, to follow the logical thread of existing ideas to its ultimate conclusion. They were investigating What would happen if you took three seemingly reasonable assumptions and insisted that all of them be true at the same time? The first assumption was that information does indeed escape the black hole, carried away by the Hawking radiation. This saves quantum mechanics, so it seemed like a good starting point. Let's call this the information escape rule. The second assumption was Einstein's no-drama rule, the equivalence principle. This states that an astronaut falling into a black hole should pass through the event horizon without noticing anything unusual. Spacetime should be smooth and empty at the edge. The third assumption was the validity of standard quantum field theory, which is our best description of how particles and forces behave. This theory works incredibly well everywhere else in the universe, so it seemed safe to assume it works near a black hole's horizon too. The AMPS team took these three pillars of modern physics and showed that they could not all be true. They created a logical paradox, a trilemma. If you hold any two of the assumptions to be true, the third one must be false. It was like a physics version of the game rock, paper, scissors. You simply couldn't have all three at once. The conflict arose from a strange and wonderful property of the quantum world called entanglement. Let's pause here to really get a feel for entanglement. It's one of the most famously bizarre concepts in physics, something Einstein himself called spooky action at a distance. Imagine you have a pair of magic coins. They are linked in a special way. If you flip them, one will always land on heads, and the other will always land on tails. Always. Now, you give one coin to a friend and keep the other. Your friend travels to the other side of the galaxy. You flip your coin, and it lands on heads. At that exact instant, you know with absolute certainty that your friend's coin has landed on tails. It's as if the coins are communicating faster than light, but they're not. They were created as a single correlated system. They are entangled. Their fates are intertwined, no matter how far apart they are. This is what happens with the particles of Hawking radiation. Let's go back to our virtual particle pair that appears at the event horizon. One particle falls in. Let's call him Bob. The other escapes. Let's call her Alice. Alice and Bob are an entangled pair. Their quantum properties are linked, just like our magic coins. If you measure a property of Alice, you instantly know the corresponding property of Bob, who is now inside the black hole. Now, let's bring in the information escape rule. For the information of our book to get out of the black hole, it has to be encoded in the outgoing radiation. This means that our escaping particle, Alice, can't just be a random bit of static. She must be entangled with all the radiation that came out before her. Think of the outgoing radiation as a long, complex sentence that tells the story of the book. Alice is the newest word in that sentence. For the sentence to make sense, she has to be connected or entangled with the words that came before. And here is the fatal problem. Alice, our escaping particle, now has to be entangled with two different things at the same time. She has to be entangled with her original partner, Bob, who is inside the black hole. And she also has to be entangled with the cloud of previously emitted Hawking radiation, which is outside the black hole. But there's a fundamental rule in quantum mechanics called the monogamy of entanglement. It's a bit like its name suggests. A quantum particle can be maximally entangled with only one other partner. It can't have two equally strong, intimate connections. It must choose. The AMPS team realized that the black hole was forcing an impossible choice. Alice had to be entangled with Bob to satisfy the laws of particle creation at the horizon. and she had to be entangled with the previous radiation to satisfy the information escape rule. You can't have both. This was the contradiction. One of the starting assumptions had to be wrong. So which one do you give up? Maybe you give up the information escape rule, but that means information is lost and quantum mechanics is broken. Most physicists find this too bitter a pill to swallow. Maybe you give up on standard quantum field theory, but that theory is so successful, abandoning it seems drastic. This left the third option, the one that the AMPS team put forward as the most logical, if terrifying, conclusion. You have to give up Einstein's no-drama rule. You have to give up the idea of a smooth, peaceful passage across the event horizon. What happens instead? To preserve the monogamy of entanglement, the universe must make a choice. It must violently break the entanglement between the infalling particle Bob and the outgoing particle Alice. And breaking a quantum entanglement bond is not a gentle process. It releases an enormous amount of energy. The AMPS paper argued that this constant breaking of entanglement pairs at the event horizon would create a seething, chaotic barrier of high-energy particles. A wall of fire, right at the place where space-time was supposed to be most serene. This is the firewall. It's the universe's brutal solution to a thorny logical problem. It solves the information paradox by creating a new, violent reality at the edge of the black hole. The information doesn't need to be encoded in a subtle way, because the infalling object never actually adds its information to the black hole's interior. It's destroyed at the gate. The firewall hypothesis is not a physical wall made of bricks and mortar. It is a boundary of pure, chaotic energy. It's a concept that is both deeply unsettling and strangely logical. Imagine you are an astronaut, falling towards a large black hole. In the old picture, guided by Einstein, you would drift peacefully across the event horizon, unaware of the point of no return. You would have a few moments of quiet freefall before your journey's end. But in the firewall picture, your journey ends much more abruptly. As you approach the event horizon, you don't find empty space. You find an incinerating curtain of reality-shredding energy. You and your ship, and the very information contained in your atoms, would be vaporized in an instant. Your constituent parts converted into a blaze of radiation that would then contribute to the outgoing Hawking radiation. Let's try a gentler visualization. Think of a soap bubble. The surface of the bubble is smooth, iridescent, and delicate. This is Einstein's event horizon. You could, in theory, pass a tiny needle through it without popping the whole bubble. Now imagine the firewall. Instead of a smooth soap film, the boundary is a crackling, hissing surface of electrical sparks, like a massive Van de Graaff generator. There is no gentle passage. Anything that touches this surface is instantly zapped, its structure and information scrambled and radiated away as a flash of light and heat. This firewall is created by the need to resolve the entanglement paradox. Let's go back to Alice and Bob, our particle pair. Alice escapes, and Bob falls in. For information to be conserved, Alice must be entangled with the radiation that came before her. But she was born entangled with Bob. To solve this, the universe severs the Alice-Bob connection. It's like a dramatic cosmic breakup. The energy released by this breakup is what constitutes the firewall. It's not a pre-existing structure waiting for you. It's a phenomenon that happens as a consequence of the ongoing process of Hawking evaporation. The firewall mechanism is a direct consequence of putting quantum information first. If you insist that information must be preserved and must escape, and you insist that the rules of entanglement are unbreakable, then the smooth geometry of spacetime described by Einstein has to give way. The firewall is the price you pay for quantum unitarity. It suggests that the event horizon is not a gentle geometric boundary in spacetime, but a real, physical, and violent endpoint. It is the place where the smooth fabric of reality tears, and from that tear, fire emerges. This idea sent shockwaves through the theoretical physics community. It was provocative. It was elegant in its logic, yet horrifying in its implications. It pit our two greatest theories against each other in a direct and unavoidable conflict. It suggested that at the edge of a black hole, there is no quiet whisper into the void. There is a roar. The proposal of a firewall at the event horizon of a black hole represents one of the most significant clashes in the history of physics. It places our two most successful theories of the universe, general relativity and quantum mechanics, into a head-on collision. At the very center of this conflict is one of Einstein's most cherished ideas, the equivalence principle. This principle, as we've touched upon, is the very foundation upon which general relativity is built. It's the idea that the laws of physics should be the same for any observer in free fall, anywhere in the universe. It means that gravity, locally, can be made to disappear. Think about astronauts floating weightlessly in the International Space Station. They are not far from Earth's gravity. In fact, the gravitational pull there is about 90% as strong as it is on the surface. So why are they floating? Because they are in a constant state of free fall. They, and the station around them, are continually falling towards the Earth. It's just that they also have a very high sideways velocity, so they keep missing it. Inside their falling frame of reference, gravity vanishes. They can do their experiments, drink their floating water droplets, and feel no gravitational force at all. This is the equivalence principle in action. Einstein extrapolated this to the most extreme gravitational environment imaginable, the event horizon of a black hole. He reasoned that an astronaut in a spaceship with its engines off, falling freely into a black hole, should also feel weightless. As they cross the event horizon, they should be in a perfect state of freefall. Therefore, they should experience no force, no radiation, no drama. From their local perspective, it should feel like floating in empty space. The space at the event horizon, according to relativity, should be no different from any other patch of empty space in the cosmos. It is smooth, continuous, and unremarkable. This is the no-drama rule we spoke of, and it is a non-negotiable prediction of general relativity. The firewall hypothesis takes a sledgehammer to this beautiful idea. It says that the space at the event horizon is not empty. It is not calm. It is, in fact, the most violent place in the universe outside of a singularity. It is a wall of high-energy quanta, a seething cauldron of particles that would instantly incinerate any object attempting to cross. For our free-falling astronaut, the experience would be the exact opposite of no drama. It would be the ultimate drama. One moment they are approaching what appears to be empty space. The next they are annihilated by a blast of energy more powerful than anything imaginable. This isn't just a minor disagreement. It's a fundamental breakdown. If the firewall exists, then the equivalence principle is wrong. And if the equivalence principle is wrong, then the entire geometric foundation of general relativity is, at best, incomplete. It would mean that space-time is not the smooth, continuous manifold that Einstein envisioned. It would mean that at the boundaries of black holes, the geometry of the universe comes to a fiery, quantum mechanical end. Let's visualize this clash of ideas. Imagine spacetime as a perfectly calm, deep lake. General relativity describes this lake with beautiful, flowing mathematics. A boat can glide across its surface, and a submarine can sink beneath it, with the water parting smoothly around it. The event horizon is just an invisible line on a map of this lake, a line beyond which the currents are too strong to return. The firewall hypothesis, on the other hand, says that this invisible line is actually a raging circular waterfall of fire. There is no smooth passage. The moment your boat or submarine touches this line, it is consumed. The two pictures of reality are utterly incompatible. This conflict highlights why physicists are so desperate for a unified theory of quantum gravity. General relativity is a classical theory. It doesn't include the weird, probabilistic nature of the quantum world. Quantum mechanics, on the other hand, doesn't include gravity. For most situations, this is fine. Relativity works for big things, and quantum mechanics works for small things. But at the event horizon of a black hole, you have both. You have an immense gravitational field, relativity's domain, acting on a quantum scale, quantum mechanics domain. It is the perfect laboratory for forcing these two theories to confront each other. The firewall is essentially a quantum mechanical effect, the release of energy from broken entanglement bonds that completely overwhelms the classical geometric smoothness predicted by relativity. It suggests that quantum effects don't just add a little bit of fuzziness to the edge of a black hole. They build a wall. This challenges the very notion of what spacetime is. Is it a fundamental, continuous backdrop to reality, as Einstein believed? Or is it an emergent property, something built from more fundamental, discrete, quantum bits of information, perhaps like the pixels on a screen? If spacetime is emergent, then it could well have seams or glitches, or violent boundaries where the underlying code breaks down. The firewall could be one such boundary. So the clash is profound. The firewall saves the core principle of quantum mechanics, the conservation of information, but it does so at the cost of sacrificing the core principle of general relativity, the equivalence principle. It forces physicists to choose a side. Which principle is more fundamental? Which one are we willing to discard? Most physicists are reluctant to abandon either. Both theories have been tested to incredible precision and have proven to be fantastically successful in their respective realms. The firewall paradox tells us that they cannot both be the complete story. The true theory of quantum gravity, whatever it may be, must somehow resolve this conflict. It must explain what really happens at the edge of a black hole, and in doing so, it will teach us something new and profound about the nature of spacetime, information, and reality itself. To truly grasp the heart of the firewall debate, we need to dive a little deeper into the gentle yet perplexing waters of quantum entanglement. It's a concept that is so central to this story, it's worth taking a moment to sit with it, to let its strangeness and its beauty wash over us. As we said, Einstein famously called it spooky action at a distance, because it seemed to defy the cosmic speed limit, the speed of light. But the spookiness is not in any faster-than-light communication. The spookiness is in the connection itself. Let's use another analogy, one that might feel a little more tangible. Imagine you have a pair of perfectly matched gloves, one left and one right. You place them into two identical sealed boxes without looking. You shuffle the boxes, so you don't know which is which. You keep one box and give the other to a friend who is about to embark on a long journey to the star Proxima Centauri. Your friend travels for years, Finally, they arrive. At a prearranged time, you both open your boxes. You open yours and find the left-hand glove. In that exact instant, you know, with 100% certainty, that your friend, 4 light years away, has just opened their box and found the right-hand glove. Did information travel from your box to theirs? No. The outcome was, in a sense, predetermined the moment the gloves were placed in the boxes. The information was shared between them from the start. They are a correlated pair. They are a single system, even when separated by vast distances. Quantum entanglement is the subatomic version of this. When 2 particles, like our Hawking radiation pair Alice and Bob, are created together, they can be entangled. Their properties, like spin, are linked. If they are created with opposite spins, and you measure Alice's spin to be up, you know instantly that Bob's spin is down. Their fates are intertwined. This entanglement is the fuel for the information paradox. As we saw, when the particle pair is created at the event horizon, Alice escapes and Bob falls in. They are entangled. This is step 1. Now, for the information about the book we threw into the black hole to escape, it must be imprinted on the outgoing Hawking radiation. This means that as Alice flies away, she can't be a generic random particle. She has to carry a piece of that information. To do this, she must become entangled with the particles that were radiated away before her. Let's call this cloud of prior radiation Charlie. So, for information to be conserved, Alice must be entangled with Charlie. This is step 2. Now we have a quantum love triangle. Alice is entangled with Bob, her birth partner, and she is also entangled with Charlie, the information record. This is where the monogamy of entanglement rule comes into play. This principle, more formally known as the strong subadditivity of quantum entropy, is a cornerstone of quantum information theory. It states that entanglement is a resource that cannot be freely shared. A particle can have a passing acquaintance with many other particles, but it can only be in one deeply committed maximal entanglement at a time. It cannot be fully entangled with both Bob and Charlie simultaneously. It's a fundamental limitation. So, the universe at the event horizon is faced with an impossible demand. The laws of particle creation say Alice and Bob must be entangled. The laws of information conservation say Alice and Charlie must be entangled. The law of monogamy says this is forbidden. Something has to give. The AMP's paper argued that the most natural thing to break is the most fragile link, the entanglement between the inside and the outside of the black hole. The bond between Alice and Bob must be severed. Imagine the entanglement bond as a delicate, invisible thread connecting 2 particles. When the universe needs to break this bond to preserve information, it's not a gentle snip with a pair of scissors. It's a violent snap. And when this quantum thread breaks, it releases its stored energy. This released energy is what creates the firewall. It's a continuous process. Every time a new Hawking particle, a new Alice, is created, it faces this impossible choice, and the bond with its infalling partner, a new Bob, must be broken. The event horizon becomes a graveyard of broken entanglement bonds, and the energy from this continuous breakup creates the searing hot wall. This is the firewall solution to the paradox. It prioritizes the monogamy of entanglement and the conservation of information. In this picture, the astronaut falling in never gets to make it inside. The information of their being is stopped at the door, incinerated, and its energy is used to create the very radiation that will carry that information away. The information never truly enters the black hole's interior in the first place. It is, in a sense, reflected at the fiery boundary. This entanglement-based argument is what makes the firewall hypothesis so compelling to many physicists. It's not just a wild guess. It arises from a very careful, logical analysis of the established rules of quantum mechanics. It shows that if you take quantum theory seriously, it has dramatic consequences for the nature of spacetime. It paints a picture where the geometry of space is not the fundamental reality. Instead, the connections between things, the web of entanglement, might be more fundamental. And where this web is forced to tear, space-time itself burns. This deep connection to entanglement also helps us understand why the firewall is such a quantum phenomenon. In a classical, non-quantum world, there is no entanglement. There is no information paradox. Einstein's smooth, gentle horizon works perfectly fine. The firewall is a purely quantum ghost, born from the spooky rules that govern the universe at its smallest and most intimate level. It is the price of quantum monogamy. And it's a price that would rewrite our most basic understanding of what it means to fall. If black hole firewalls are real, the implications stretch far beyond the arcane world of theoretical physics. They touch upon the very nature of reality, space, and time. The existence of a firewall would force us to abandon some of our most deeply held beliefs about the cosmos and replace them with something far stranger and more volatile. It would mean that the universe, at its extremes, is not the smooth, continuous place we thought it was. First and foremost, it would mean that Einstein's beautiful, geometric picture of gravity, while incredibly accurate for describing planets and galaxies, is not the final word. The idea that space-time is a fabric that can be bent but not torn would be proven wrong. The firewall represents a tear, a seam, a violent edge to the fabric of reality. It suggests that space-time as we know it is an approximation, a low-energy illusion that breaks down in the face of extreme quantum conditions. This is a profound shift. For a century, we have thought of space-time as the stage on which the play of the universe unfolds. The firewall suggests that the stage itself can catch fire and burn away, revealing something more fundamental and perhaps more chaotic underneath. Let's take a moment to visualize this. Imagine you are walking on a beautiful, solid-looking floor. It's smooth, polished, and you trust it completely. This is the space-time of general relativity. But the firewall hypothesis suggests that if you walk towards a certain point in the room, the event horizon, the floor beneath your feet, will suddenly dissolve into a raging inferno. The very ground of being is not as solid as it appears. This has enormous implications. It could mean that space and time are not fundamental, but are instead emergent properties, woven from a deeper layer of quantum information, much like the image on a computer screen is made of tiny, discrete pixels. In most cases, the pixels are so small and the image so smooth that you don't notice them. But at a place like an event horizon, you might be seeing the pixels of space-time itself, glitching out and creating a fiery error message. This leads to the second major implication, which concerns the holographic principle. The holographic principle is another fascinating idea from the world of quantum gravity, championed by physicists like Gerard 't Hooft and Leonard Susskind. It suggests that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space. It's like a hologram, where a three-dimensional image is encoded on a two-dimensional surface. This principle has been a guiding light for many theories of quantum gravity, including string theory. It beautifully connects the amount of information in a region, its entropy, to the area of its boundary, just as Jacob Bekenstein and Stephen Hawking found for black holes. The firewall throws a wrench into this elegant picture. The holographic principle relies on a smooth connection between the interior of a space and its boundary. But the firewall suggests that the boundary itself is a special violent place, disconnected from a smooth interior. If an observer is destroyed at the boundary, what does it mean for their information to be encoded there? The firewall complicates the simple holographic dictionary that physicists were hoping to find. It suggests that the relationship between the bulk and the boundary is far more complex and violent than a simple hologram. Thirdly, the existence of firewalls would fundamentally change our cosmic narrative. Black holes would no longer be the universe's ultimate vaults, silent keepers of secrets. They would become the universe's ultimate incinerators. Anything that falls towards them would be brutally erased at the perimeter, its essence recycled into a random spray of thermal energy. This is a less poetic, more brutal vision of the cosmos. The quiet, majestic darkness of a black hole would be replaced by a hidden, defensive fury. This might sound like a bleak prospect, but in physics, such crises are often the seeds of progress. The firewall paradox, in all its thorny difficulty, is incredibly valuable. It's like a bright, flashing warning light on the dashboard of our understanding. It's telling us, warning, your current theories are incompatible. A fundamental rewrite is required. It points with a fiery finger to the exact place where our knowledge breaks down, the event horizon. It's a signpost for the next generation of physicists, guiding them towards the questions they need to answer to find a true theory of quantum gravity. So, while the idea of a firewall that burns reality might seem destructive, its role in science is actually constructive. It forces us to confront the deepest paradoxes we have. It challenges us to be more creative, to question our most basic assumptions. Does a firewall really exist? We don't know. There is no way to test it experimentally with our current technology. It remains a theoretical battleground, but the debate it has sparked is pushing the boundaries of human knowledge. It is forcing us to ask questions about whether spacetime is doomed, whether information is truly fundamental, and what strange new principles might govern a universe where the laws of the very large and the very small must finally learn to get along. The fire may be hypothetical, but the intellectual light it has generated is very real. The firewall hypothesis, with its stark and fiery conclusion, did not land in a quiet, accepting physics community. It ignited a fierce and fascinating debate that continues to this day. The idea that Einstein's beautiful, smooth spacetime could have such a violent edge was deeply troubling to many. It felt, to some, like a brute force solution, a cure that was worse than the disease of the information paradox. And so, physicists, in their creative and relentless way, began to search for alternatives. They looked for loopholes in the AMP-C argument, for other paths that could lead out of the paradox without having to burn down the equivalence principle. One of the most prominent alternatives comes from a pre-firewall idea that was updated to respond to the new threat. This is the concept of black hole complementarity, originally proposed by Leonard Susskind and others in the 1990s. Complementarity is a subtle and mind-bending idea. It suggests that there is no single, objective truth about what happens at the event horizon. Instead, the reality you experience depends on your point of view. Imagine our astronaut, let's call her Amelia, falling into the black hole. And we have her friend, Ben, watching safely from a distant spaceship. According to complementarity, Amelia and Ben experience two different, yet equally valid, realities. From Ben's perspective, he sees Amelia approach the event horizon, slow down as time dilates, and become flattened and scrambled on the surface. He then sees her information slowly radiated back out as Hawking radiation over trillions of years. In Ben's reality, Amelia never truly crosses the horizon. She is absorbed and re-emitted at the boundary. From Amelia's perspective, however, things are completely different. She follows the no-drama rule. She feels nothing special as she crosses the event horizon. She floats peacefully in her spaceship, seeing the universe outside her window speed up and continues her journey inward. In her reality, she passes smoothly through the horizon, and her information is with her inside the black hole. The principle of complementarity states that both of these stories are true. They are complementary descriptions of the same event. The paradox is avoided because no single observer can ever see both outcomes. Ben, from the outside, can never see what's inside the horizon. And Amelia, once she's inside, can never send a message back out to tell Ben that he was wrong. Since there is no experiment that can be done to prove one view is right and the other is wrong, the contradiction is never brought into the open. It's a form of cosmic plausible deniability. The Firewall argument was a direct attack on this peaceful, if strange, picture. The AMPS team argued that complementarity wasn't enough to solve the entanglement problem. Even if Amelia doesn't know her information is also being radiated out, the quantum entanglement must still be respected. However, proponents of complementarity and related ideas have been working on ways to save it. One of the most exotic and exciting of these is a proposal known as A equals EPR. This is a conjecture put forward by Leonard Susskind and Juan Maldacena, another giant in the field. It's a very pithy equation that connects two seemingly unrelated ideas from physics. EPR stands for Einstein, Podolsky, and Rosen, the authors of the famous 1935 paper that first described quantum entanglement. So, EPR represents entanglement. A stands for Einstein and Rosen, who in the same year discovered a mathematical solution in general relativity that looked like a bridge or a tunnel through spacetime. We now call these wormholes, or Einstein-Rosen bridges. The A equals EPR conjecture proposes that these two things are, in fact, the same. Every entangled pair of particles is connected by a tiny, microscopic wormhole. It's a radical idea. The spooky action at a distance of entanglement is actually a physical, albeit non-traversable, connection through the geometry of spacetime. How does this help with the firewall? It suggests that the entanglement between the outgoing Hawking particle, Alice, and the infalling particle, Bob, is itself a wormhole connecting the interior of the black hole to the region just outside. This wormhole might provide a backdoor for the information to escape, resolving the paradox without the need to violently break the entanglement bond and create a firewall. It's a highly speculative but deeply beautiful idea that attempts to weave the strangeness of quantum mechanics directly into the fabric of spacetime. Another major class of alternatives comes from string theory, our leading candidate for a theory of quantum gravity. In string theory, fundamental particles are not points, but tiny, vibrating strings. One proposal from this field is the fuzzball model. The fuzzball idea, developed by physicists like Samir Mathur and his collaborators, suggests that black holes don't have a classical event horizon and a singularity at all. Instead, what we call a black hole is actually a giant, messy, star-sized ball of vibrating strings and other quantum fuzz. Imagine a ball of yarn. From a distance, it looks like a solid, fuzzy sphere. But up close, you see it's an incredibly complex tangle of individual strands. The fuzzball proposal says a black hole is like this. There is no empty space inside and no sharp boundary. The object has a real physical surface, though a very fuzzy one. When you throw your book at a fuzzball, it doesn't pass through a horizon. It hits the surface and its information gets absorbed into the complex vibrations of the strings. The fuzzball then radiates thermally, just like any hot object, and the information is naturally encoded in that radiation. In this picture, there is no information paradox to begin with, and therefore no need for a firewall. The no-drama rule is violated, but in a much gentler way than with a firewall. You wouldn't be incinerated by a wall of fire, but you would bump into a wall of fuzz. These are just a few of the leading ideas in a vibrant and ongoing debate. Some physicists argue that the AMPS calculation made subtle assumptions that might not be correct. Others believe that the problem lies in our understanding of how quantum gravity works in a dynamic, evaporating spacetime. There are ideas about black hole remnants, tiny, stable nuggets of information left over after the evaporation, or complex computational theories suggesting that the information is there, but it's just incredibly difficult to decode. What is clear is that there is no consensus. The black hole firewall is not an established fact. It is a hypothesis. A profound and powerful what-if that has forced the world of physics to confront its deepest contradictions. It remains a puzzle, a cosmic cone posed to us by the universe. The answer, when we find it, will not just tell us about the fate of an unlucky astronaut. It will tell us about the fundamental ingredients of our reality. It will be the next great chapter in the story we tell ourselves about the cosmos, a story that began with Einstein's gentle curves in spacetime and has now led us to a potential fire at the edge of forever. And as we drift off to sleep, we can leave the world's brightest minds to continue their work on this beautiful, fiery problem, confident that the search for understanding in itself is one of the most wonderful things in the universe.